Okay. So while I am no longer sick, I am still recovering. So it's very easy for me to get out of breath. If I did not meet, if you needed to meet with me and I could not meet with you over the past couple days, because I've been sick, I'm sorry about that inconvenience. I'll try to meet with you as soon as possible. I understand that plenty of you are still asking for more time on the Cheers Hangman assignment. That's fine. Just please don't try not to take too much longer on that. Okay. Give me 1 sec to adjust the lighting in the room. So yeah, if you need more time on the hangman, yeah, that's fine. Apparently, there's not. That said, I am going to discuss the sorting algorithm homework. Okay, the one that just got proposed. This one is going to be, so this one is a bit different. Mainly because there's very little, there should be very little coding or original coding done on your part, except for modifying an algorithm that already exists. Okay, so you can use any programming language for this one. All right, so you are to implement insertion sort, quick sort, and one other sorting algorithm. So this is the first step. Implement quick sort, insertion sort, and one other sorting algorithm of your choice below. Either shell sort, merge sort, heap sort, or TIM sort. These are all sorting algorithms that are covered in the textbook. Shell sort is a weird one, but it's really cool because we don't know we actually don't know yet what its optimal runtime is. Check out its Wikipedia page. Merge sort is one of those, and quick sort are used very extensively in programming libraries, but TIM sort has kind of taken over where merge sort used to be. TIM sort is done. It was introduced in a paper, implemented in Python as an internal sorting library for sorting operation for Python, and then it quickly got used by other programming languages. So pretty much anytime you call an internal sorting algorithm, it will be quick sort or TIM sort that it's performing it on. Java uses both. It depends on whether you're sorting objects or primitives. Okay, just check the documentation of it. Specifically, Java uses something called a dual pivot quicksort, which I don't go over because that is extremely advanced. And by the way, when I talk about quicksort, I mean an in-place quicksort algorithm that I show in the videos. So if need be, you can check out the slides, which are on the Canvas webpage, and get the code from there. You can also, again, one great resource besides Wikipedia for source code is also Rosetta Code. Okay, Rosetta Code is one of those, it has basically a bunch of basic programming language, basic algorithms. So let's search for insertion sort, sorting algorithm, insertion sort. And then go and look for the algorithm of your choice. Assuming it loads. Why aren't you loading? There we go. Sorry, look for the programming language of your choice. So here I can look in Python for insertion sort. And it has a few different ways to do it in Python. If we look for Java, right, here it is in Java. Using some built-in algorithms, it warns you that it's not stable. So you probably want to do something like this, okay, for insertion sort. Okay. So this is, and so why am I, so, you know, and if you get this from a website, that's fine. That's actually kind of the objective of this website, of this assignment. So be sure to cite wherever you get it from, okay? How do you cite it? Just put the URL in the comments, right? That's all you really need to do for this class. Okay. The second part of it is now that once you get these, you need to modify these sorting algorithms to keep track of the number of comparisons performed, the number of exchanges performed, and the total runtime of the algorithm. All right. So they need to report back somehow how long they take. Okay. So first, before we talk about what reporting back some data, what is a exchange and what is a comparison? A comparison is whenever we check if two things need to be sorted. Okay. Sorry, if two things are out of order. Okay. So here, when we check if AJ is greater than value, we're checking if AJ needs to be moved out of the way here. Okay. And that is what we call, that is a comparison. Okay. An exchange is whenever we actually move data around. So in another sorting algorithm, let's say all the way up to bubble sort. Do they have bubble sort here? A friend who says we should never use bubble sort ever. We should stop teaching it in programming classes because it's so bad. Okay. Java, bubble sort. So here, anytime we do this compare to check, okay, that would be a comparison here. And anytime we do a swap operation like this, that would be an exchange. Similarly for, and one of my favorites to talk about here is selection sort, another kind of terrible algorithm, but possibly the best one to talk about why we care about exchanges and comparisons. Okay. So selection sort looks like this. What it does is that it looks at the first index and says, okay, the smallest item needs to go there. Let me find what the smallest item is and put it there. Okay. So it searches through all the items. It searches through all n items. That's what this loop does. Each item, it checks to see if it's the smallest. If it's the smallest, it updates it. And then now that it's found the smallest, it swaps what it found the smallest with whatever index it's looking for. Then it looks for the second smallest item, starting at index 1. Then the third smallest item starting at index 2. So you get so basically what you do is you look through all the items, find the smallest, move it to the front. Look for the second smallest item, move it to index 1. Third smallest item until we get to the end. Now, what's great about this is that each iteration takes O of n time, right? You have to check n items, then n minus 1, then n minus 2 items, n minus 3. But we do one swap. Now, when we talk, so we do a total of n squared comparisons and O of n swaps. But we say selection sort's time is O of n squared. This is because in general on computers, comparing two items to see if the one is less than or greater than the other is more expensive than moving data around. Now, the reason for this is because A, it can be more expensive, but also we don't know necessarily what we're comparing. If we're comparing like one object to another, and these are very complicated objects with, you know, a very complicated compared to operation, it could be extremely expensive. Whereas moving two pieces of data around, that's just copying bits from one place to another, that's pretty easy for the computer to do. Okay. On the other hand, why do we care about exchanges then? Well, because sometimes we aren't doing sorting algorithms on the computer. If we're moving boulders around for some reason and need to line them up, we probably want to care about the amount of effort we have to expend physically, right? Versus the amount of comparisons we have to do. In that case, exchanges are the more complicated, more expensive operation, so we want to minimize that. So selection sort is superior if you want to keep your exchanges to a minimum. That's why we still teach selection sort, even though it's got a terrible runtime, and the runtime is always terrible on a computer. So we want to keep track of, so this is an exchange. Each of these if statements is a comparison over here, but not every if statement is a comparison, right? Only if you're checking to see if things are out of order. Okay, so how should you modify this algorithm to do that? So there's two ways, there's a couple of different ways you can do that. One is you can have a static variable outside of the function, number of comparisons, number of exchanges, and just increment them whenever you see that. And then every time you run the algorithm, you reset those variables. You reset it to 0 each time you do a new run. Okay. The other way to do this is you create a data object, which has only 2 fields, a data data.exchanges and data.comparisons. You pass that in as an argument, and each time you compare, you just increment the data object instead of the static variable, and then you can return that data object. Or you don't even need to, because if you created it outside the function, that will get modified, and then you can just simply print out the data. This I find to be a more useful approach and a bit easier, because what you're going to need to do is that you're going to need to create multiple runs, right? Once you've multiplied the item, I want you to gather data. So once you've implemented the algorithm, I want you to gather data. So what we need to do, so what I want you to do is like test it on different size lists of random size, random values. So decent test might create, we might create random lists of 64, then you might test it on size 128, then test it on size 256, and set it on size 512, then 1024, et cetera, et cetera. Make sense? Until it becomes like unfeasible. And you'll want to do multiple runs and average them out, like multiple runs of 64, multiple runs of 128, multiple runs of 256, to make sure you didn't get like a skewed data point. Okay, makes sense? So like 5 runs of each of these. Generating a random integers of each size random list of each size shouldn't be too difficult, by the way. You'll want to output your data to a file. Honestly, you can either just write it to a file physically, or you can just simply copy paste your print output and put it into a CSV file. I'm not too picky, but the point being is that you want to put it into a CSV file or an Excel file for the final part, which is plotting your data. I want you to plot that data in a graph or a really well formatted chart to show me that, okay, we can see here that insertion sort has an O of n squared runtime in terms of comparisons, and merge sort has n log n very clearly, So I want you to basically see that I want you to be able to demonstrate this growth rate to somebody who is in a way that's very evident to people who understand data but might not necessarily be a programmer. Okay. So the grading. So just simply implementing these algorithms is worth 70 points. So even if you can't modify these algorithms that well, please do that. 15, so, just simply implementing these algorithms, which shouldn't be too hard because, they're available online, is worth 70 points out of 100. So even if you can't do that, I'm giving you free points here. Do it. 15 of the remaining points is the data collection, modifying the algorithm, right? And then the remaining 15 points is doing the data presentation. All right, so what should you care? So this is a good chance to tell you what you should study for the final exam in terms of sorting algorithms. Okay, I can guarantee you, since I write the final exam for all the classes, that insertion sort, there will be a question about the sorting algorithms that I typically ask a question about are insertion sort, quick sort, and merge sort. It's almost as though I'm kind of implying that right there. So know how those work, just know how those work and know what the runtimes are and know what their use cases are. Like, why would I want to bother using insertion sort when quick sort and merge sort exist? With insertion sort, by the way, the answer is because it still runs very fast, faster than quick sort and merge sort for very small sizes, like 64 or lower. Because remember, recursion does incur some overhead, and quick sort and merge sort are both recursive. Insertion sort is not recursive. So long as you're at a low size, insertion sort's actually the way to go. In fact, the optimized version of one of the ways the book suggests optimizing quicksort is that it calls insertion sort for subarrays that are less than 64, and to sort that rather than trying to sort it itself. So insertion sort is very efficient for that. There's other reasons that I go to in the videos, but also knowing how quicksort and merge sort work. So yeah, that's this assignment. It's not necessarily too difficult. It can be a lot to think about, especially in terms of organizing. That's the part about this is organizing. And then also working in like just basically fiddling around with Excel. All right, any questions on this one? All right, exam 2, how was it? Easier? Okay, how was the group portion, by the way? Okay, I haven't had the chance to look at the exams yet because I was busy. Because my family had been sick and then I got sick, I hadn't had a chance to grade the 1051 exam. So now I should be able to grade your exams, and I'll be getting the group exams as well today. So expect that by the end of the week. Your grades for this one. So yes.
There were some good questions in the group exams.
What?
There were some good questions that are in the group exam and the individual exam.
Oh, so between this, there were some questions that were the same in the solo and the group, are you saying? Yeah, that was intentional. Okay, that I only wanted to introduce some new questions and I wanted to give the chance to have immediate feedback on what I considered to be the harder questions for the solo question. Make sense? So like specifically those tree questions. I think it was like 2 tree questions. The group exam was 2 of the tree questions you saw before, the Huffman question and the dictionary question, sorry, map question, right? Yeah, so, all right. I will try to get that to you as soon as possible. All right. So I'm going to go ahead and stop sharing, stop recording. Oh, actually, there is one more thing I want to talk about, though, before I completely move on. There is something, because otherwise you're never going to see it here, which is that I just mentioned that we mentioned about all these sorting algorithms work with comparison, but basically we care about how the number of comparisons in determining runtime. But not all sorting algorithms actually care about comparing things. Some sorting algorithms actually do no comparisons to sort things. One good example of this is an old sorting algorithm, a really old one called radix sort. And I may wait to go over this on Thursday, but because I want to be able to get the chance to help people. But in case I don't get the chance, take a look at radix sort and look at its weird runtime. It's OWN, where W is the length of the key. So if we're talking about longs, if we're talking about sorting integers, then W is 32 because we've got 32 bits to sort between. And it's a very interesting runtime as a result. If you're sorting words, then W is the length of your longest word. And it's weird because it uses queues to do sorting. But the reason it doesn't do any comparisons is because you didn't have machines back in you needed a way to sort things back in the day that a machine could do without comparing anything. So I'll discuss that on Thursday. All right, stop sharing, and now I'll start recording.